Hello, welcome again to Noise Control and its Management. Today is the second day of the 9th week of this course, and what we plan to discuss today is the noise coming from motor. Specifically, what we will be discussing in detail is to how to estimate the sound power level LW as it emanates from different types of motors. So, what we will discuss today is motor noise. Now, what are motors? Motors are basically machines which convert electrical energy into mechanical energy, and a typical motor has a winding inside it which rotates, and that is called the rotor. And this winding, it rotates in a static magnetic field, and that is called a by static I mean a non-moving mechanical part which has the winding. So, this rotor moves in a stator. Okay. Now, the noise, so as I said, when we want to understand what kind of noise comes from different machines, we have to understand some basic working principle and some details of that particular thing, because that will help us give some better understanding. So, noise from motors is attributable to several phenomena. So, the first thing is noise from windage. Okay. So, what is windage? Essentially, suppose you have a motor, and of course, this is the shaft of the motor, and this shaft is rotating on this axis, and then of course, there is some electricity going in, and because of electromagnetic interactions the rotor moves, and that motion is transmitted to the shaft which delivers power to wherever we want it. There is a lot of heat generated in it, because a lot of current goes in the windings, and the current windings have resistance. So, there is a lot of I square R loss which is generated in these motors, even though motors by themselves are very efficient machines. Sometimes the efficiency could be as high as 95-96%, but even then, even if 3-4% of the overall energy gets converted into heat, sometimes the power rating of these motors could be 400-500 horsepower. So, 5% of even a small that large number can generate a lot of heat, and the motor has to be cooled, all its windings and the internal mechanism, it has to be cooled, otherwise it can destroy itself very fast. So, what happens is that there are two ways to cool the motor. In one way, the air blows on the outside, and in other, so you have fins on the outside, and these as air blows on from the outside, they take away the heat and it is cooled. In other cases, air is also fed inside the motor to cool it down. Now, as air blows through the motor with outside and or inside, it is basically wind blowing across some components. So, that is the noise because of this effect is called windage noise. Okay. And this noise, so this is the first type of noise, and this noise is of two categories. Part of this noise is highly tonal. Tonal in component, because each time the rotor cuts across a particular wind or wind cuts across a particular winding, it gets pushed by a certain amount. So, that happens at a constant frequency. So, that is why part of the noise is tonal, and then other part is broadband. which means all the frequencies are present, and that is because of eddy losses and vorticities as wind blows past different obstacles. So, this is the first type of noise. The second type of noise is because of rotor. Okay. So, consider a rotor. Suppose the rotor has two. So, how does a rotor looks like? So, it is like a moving, it is the cross section of the rotor is something like this. And suppose when it is rotating, each time it rotates, each time a blade passes a particular area, a puff of air gets generated. Okay. So, because of the rotary motion of rotor, if the rotor was not moving, then that will not happen, but because the rotor is moving, each, you can call it blade, but these are not blades, these are some short metallic things popping out from the mean surface. So, each time a particular rotor's element moves past a certain point, it generates a puff of air, and it depends on the number of these slots and also the RPM, and this rotor motion is highly tonal in nature because of this. Okay. The second thing, then the third component is the interaction electromagnetic between rotor and stator. Now, this rotor moves in a stator, okay, and what is, so the stator is, so I have just increased, so this is I have amplified the gap between the stator and the rotor. Typically, it is very small to improve the efficiency of the machine. So, this gap is negligible, but the stator looks something like this. And pardon my drawing, but I hope you get the idea. Okay. And this gap is very small. I mean, the smaller the gap is, the better and the more efficient the machine becomes. So, this gap is very small. Now, what happens is that in the stator you have a strong magnetic field, and this rotor is moving in it, and rotor has metallic ferromagnetic components. So, as these components come close and go away from the magnetic field, there are contractions and expansions happening in the whole structure, and the frequency of those expansions and contractions because of electromagnetic interactions happening is dependent on the number of these blades, the number of these slots, and also the RPM. So, then because of this thing, this is also very tonal in properties. The fourth one is changing magnetic flux density. Changing magnetic flux density in stator. So, in this whole area, this is our stator, the magnetic flux density changes, and because you have it is, this whole thing is immersed in ferromagnetic parts, where the whole thing contracts or expands because of change in magnetic flux density. Okay. When magnetic flux becomes more strong, contractions are higher. When it becomes weak, things come back to their original position. So, there is lot of contraction and expansion happening because of magnetic flux density in the stator. So, this is because of dimensional changes happening. And this is again tonal noise. See, this first guy, it was not about expansions and contractions, rather because the rotor is moving inside the stator, sometimes it comes close, sometimes it goes away, and when it comes close it experiences larger electromagnetic forces, because of those forces it is rotating, and so these forces, because of electromagnetic interactions, they are also changing cyclically. So, that is why this noise gets generated, and this noise gets generated because ferromagnetic particles, materials and elements, they shrink and expand, and as they shrink and expand, noise gets generated because it pushes out air. The fifth component of noise is because of dynamic imbalance. So, these two guys are because of EM effects, this is because of mechanical effect, this is because of mechanical reasons, this is also because of mechanical reasons, dynamic imbalance. So, what is dynamic imbalance? So, suppose this shaft and the rotating parts are not perfectly symmetric about their axis, maybe they are slightly off balanced, and when they are off balance they will vibrate crazily at very large amplitudes, and that will generate a lot of noise. So, this is again tonal, and the last one is bearing noise. So, what is the deal about bearing noise? Because all these moving parts are resting in bearings, and when you rotate, the bearings also rotate, and in the bearings you have little balls, they are also rotating, and they have this type of noise. So, there is bearing noise. Okay. So, it is important to understand what different types of reasons are there which create generation of noise. Okay. The second thing we will like to understand is what types of motors are there. Now, you can classify motors in all sorts of ways, but today we will focus on a classification which is related to noise production. So, from that standpoint, there are two categories of motors. The first one is drip proof motors. And they are known as DR-PR motors. So, what is DR and PR is from the proof, DR-PR motors. Okay. What happens in these motors? These motors, the air flows outside the motor, it flows outside the motor and over the body. Okay. So, there may be an external fan which is attached to the casing of the motor, and it blows air over the motor's casing. So, it goes there. The second category of motors are known as totally enclosed fan cooling motors. In short, TEFC motors. Here the encasing, there is an internal fan in the motor, and that pushes the air, and that makes sure that all the windings and internal things get cooled down. So, based on these two things, the noise generated by motor gets heavily influenced. Okay. So, we have DR, PR and then we have TEFC, where we have an internal fan which pushes air and it actually cools the whole thing. So, now what we will do is, our original goal is to compute LW, because if I know LW I can calculate LP. So, we have to figure out what is the value of LW. Now, it happens that lot of people have done experiments and they have come up with some empirical relations, but not for LW, but they have come for LWA, A weighted. That is why it is important to understand the concept of weighting. So, for DR-PR motors, LW A weighted, so this is A weighted, is equal to 65 dBA if the horsepower of the motor is less than 7. So, this is an important condition. If it is less than 7, then in a lot of cases people have observed, and this is what they have come up with. If it exceeds 7, then we have, you can estimate the noise through this relation, 20 log of the horsepower of motor plus 15 log to base 10 of NR, okay, minus 3 if HP exceeds 7. And what is NR? This is RPM. So, it is important to remember, sometimes we use RPM, sometimes we use rotations per second. So, this is the relation for DR-PR motors, drip proof motors. For TEFC motors, LWA is equal to 78 decibels A weighted if horsepower is less than 5, if it is less than 5 horsepower, or if the motor produces more than 5 horsepowers, then it is 20 log of 10 of horsepowers plus 15 log to the base of 10 NR plus 13 if HP exceeds 5. So, there you have it. So, now we have the relation for LWA for both the motors. Okay. For DR-PR motors, if we know its RPM and the horsepower, we can estimate the sound power level, but what type of sound power level? A weighted, and what we are really interested in is LW. So, to figure out what is the value of LW, we use some conversion factors. So, to get LW from LWA, we use the following relation. And what is the relation? LW is equal to LWA minus a factor known as X, okay, minus X. And how do we find out X? So, value of X from this table, and I will just write the table, it is not very complicated. So, in the table I have two columns, power in horsepowers of the motor and the value of X. So, if it is 1 to 250, the value is 1.1. If it is 251 to 300, it is 1.2. If it is 301 to 400, it is 1.3. If it is 401 to 450, it is 1.5, and if it is 451 and above, then it is 1.7. So, first you compute LWA for a motor, from this table then you compute LW, and then this LW will help you estimate the sound pressure level at a distant point. And the last thing is, so this tells us how to calculate LW. So, with this understanding we can, and please understand that all these values of LW are not exact values, they are just giving us some broad estimate of the sound power level. Suppose you are developing a factory and you have to figure out what will be the approximate sound power level, this will give you some estimate. Okay. Later you will have to do some detailed measurement to actually find out actual values, but this will give you some broad idea, rough idea as to what will be the value of LW. Now, in a lot of cases we are not only interested in finding out LW, but we also are interested in what is the energy content, sound power level in different octaves, right, in different octaves. So, if we want to estimate sound power level in different octave bands, and we will call it LW oct, then what do we do? Then we use two steps given below. Okay. Step 1, actually it is not two step, it is just a single step. We use the step given below. So, the step is, what is the step? LW oct. Now, these are different octave bands, right, and the industry standard octave bands which we have discussed is 63 hertz, 125, 250, 500, 1000, 2000, 4000, 8000. So, this LW oct will have 8 different values or it can be more if we are interested in more number of octave bands. So, LW oct equals LW, but we do not use in this case LW, we use the A weighted value, and A weighted value we already know how to calculate it, minus a factor F1, okay, and this factor F1 will vary from one frequency band to other frequency band. So, it will vary from one frequency band to other frequency band. शुरू कर दें? हाँ. It will vary from one frequency band to other frequency band, this F factor F1, and you would be wondering what kind of numbers are these factors. So, this F1 is from a table which I will show you in a while. Okay. So, let us look at this table. Okay. So, this is the factor which we call F1. So, what you have in this table is, and this is for electric motors, the horsepower of the motor 1 to 250, 300 to 400 and so on and so forth. There is a gap, of course, 250 to 300 we do not have data, maybe you can look around or you can do some approximation or interpolation from there, from this. But for different octave bands with central frequencies, these 63, 125 and so on and so forth, these are the values of F1. So, you can pick up this value F1 from here and put it back in our equation, and what you will get is the value of LW for each specific octave band for different octave bands. So, this is how we will do it. So, I think what we will do is we will conclude our lecture for today, and we will actually continue this discussion tomorrow also, and specifically we will do a small example so that things become clearer. So, that concludes our discussion, and we will meet once again tomorrow. Thank you.